most lessons, we learned about different transformations. So we learned that we can change the vertex form of a quadratic and we can make it go up and down and skinnier and wider and flip upside down and things like that. And so we're going to be talking about these transformations for the next couple lessons. And that was sort of just our intro yesterday. So some of this may seem familiar from the Desmos lesson, and that's a good thing. And so today we're specifically going to talk about shifting quadratics. And so if you guys remember back in geometry, we learned some different things called like that we could do to different shapes. Or different transformations we could do to different shapes. So we could reflect them across the line. We could make them larger or smaller by dilating them. We could spin them and rotate them, and we can just shift them around. So we can actually do all these same things with quadratics and with different functions. But we're going to focus mainly today on translation, which is like the shifting up and down and back and forth. One thing we won't look at is rotation. That's a little bit out of our league for right now. But we're going to learn about these different transformations and how we can apply them to functions rather than just shapes like we did in geometry. And so if we consider the parent function, which the parent function that we learned about yesterday was the original function or the original quadratic that we shape all of our other quadratics after. So the parent function is sort of like the basic original quadratic, and all our other functions are just a transformed version of this parent. And so our original quadratic is y equals x squared, and it's this graph we have next to us. And our graph currently has 5 distinct points on it. It has an infinite number of points, but the ones we can see are these 5 ones. So we have our vertex, which is 0, 0. We have 1, 1, negative 1, 1, 2, 4, and negative 2, 4. These are the 5 points we have in our graph that we're going to look at right now. And so we're going to make a new graph, or a new quadratic. And how we're going to do this is we're going to take each of these points from our original, and we're going to shift them up 2. And so I'm going to take my other color, or you can take your colored pencil, and we're going to look at our vertex, and we're just going to go 1, 2, and we're going to move it up 2 spaces. I'm going to go to my point of 1, 1, and I'm going to shift it up 2. So I'm going to go 1, 2, and move it up 2 spaces. And go to 2, 4, and shift it up 2, just like we did with all the others. Up 2 spaces. And point. Negative 1, 1. We're going to shift up 2 spaces. And then our last point, just like all the others, we're going to bounce it up just 2 spaces. And now we have these new 5 points that are all just up from our last points. And we can sort of connect the dots between these 5 points. And now we have a new quadratic that was shifted up. The whole quadratic was just shifted up 2 spaces. And so, thinking back to yesterday in our little sort of discovery activity we did on Desmos, does anyone know what the vertex form of this quadratic may be? It's okay if you don't. Or Bradley, do you have a guess? Yeah, so it's going to be y equals x squared plus 2. So we just took the whole graph and we shifted it up 2. So if we look at the point 1, 1, which was this little point right here on our graph, what point corresponds to that on our new quadratic? This one right here, the one that we shifted up 2 from it. And so if we look at the coordinates of our new point is 1, 3. And so if we look at the x and y coordinates of these graphs, what is different between 1, 1 and 1, 3? What's something that's different about them? the y coordinate. So the y coordinate got changed up 3, or up 2, I'm sorry. Y went up 2. Let's see. What happened to the x's? Tiffany? So the x's stayed the same. And so when we shifted our graph up 2, we shifted all of our y coordinates just up 2, and that was our new quadratic. So all of our points, all the y's for them got shifted up, but the x's stayed the same. Okay. Now we're going to do a similar thing, except we're going to move it to the left too. So just like we did with our first graph, and we looked at each point and we specifically moved each point to the left, or to up to, we're going to specifically move each point to the left too. And so we have our 0, 0 vertex, and we're going to shift it to the left too. We're going to shift negative 1, 1 to the left too. Negative 2, 4 to the left. 1, 1 goes to the left. And if you want to get a different color, you can swap colors with your neighbor. But if you can distinguish them. And then our last point. And so we have another 5 points that are the same, or that were similar to our original, but we just moved the whole graph over to the left. And so as soon as you get your 5 new left points, you can connect the dots and get a new quadratic. That's the same shape and everything of our old one. We just shifted the whole quadratic to the left by 2 spaces. So does someone want to take a guess on what the vertex form of this new quadratic might be? Matt? Yes. Yeah. Yeah. So it's y equals x plus 2, and the whole quantity is squared. And so you may remember that from Desmos, you may not. But when we shift to left and right, it's on the inside of our square. And so we can look at the point negative 2, 4 from our original graph. And we can look at the one that's shifted to the left of it, 2, which is our corresponding point. So the coordinates for this point is negative 4, 4, if we look on our axes. So what do you guys notice about the x coordinates between these 2 points? Is it the same? Is it different? And if so, by how much? Yeah. So the x was subtracted by 2, or was 2 less than our original. And by the original, that's our parent function. And what happened to the y's? With negative 2, 4 and negative 4, 4. Oscar? So the y stayed the same. So when we shift the graph up, our y's change, but our x's stay the same. And that means like up and down is the same. If we shift our graphs left and right, our x's change, but our y's stay the same. And so we're going to generalize this a little bit for any of our quadratics that we run into. And so as a rule, we say g of x equals f of x plus c when the graph is translated up c units. C is just a constant. It's any number. It could be 2, it could be 3, 4,000. So if we were to go up 4,000, we would say f of x plus 4,000. So if the graph is translated down c, we would use the rule h of x equals f of x minus c. So if we wanted to shift to the right by c units, can anyone take a guess on what our f of x might look like? Oscar? Yeah, it's going to be x minus c is if we shift to the right by c units. And if we were to shift to the left by c units, it's going to be x plus c. And when I say shift, I see it says translated on your paper. Shift and translated are words that we would use interchangeably. I think we'll probably use shift more frequently, but translated is the same thing. So translated can mean up and down or left and right, and shift is the same thing. And so now you should have a transformation rules chart that should look a little bit like this. And we can now fill out the first 4 columns of our transformation rules chart. So this rules chart is something that we'll constantly be coming back to throughout this unit, because we'll be learning about the different types of transformations like dilation and shifting today and reflection, though like what we learned in geometry. So we're going to be learning all of these different ones for these quadratics. And so we want this transformation rules chart to be something you can keep looking back to and keep turning back to help you study or to help you remember these transformations. So this first one, we're adding c, and so we're going to shift up c. And then if we were to subtract c, we're going to shift down by c. If we were to add c to the inside, or add 2 to the inside, as the example says, we're going to go shift left by c. If we were to subtract c on the inside, we shift right. So something you might notice is that when we're going up or down to these two, our transformation is on the outside of our function. So we have f of x plus c. So this is on the outside. So if we're doing a transformation on the outside, it's going to shift us up or down. And if we look at our left and right, this is happening on the inside of our function. So it's inside our f of x, or it's inside our square. And so if it's happening on the inside of a function, we're changing that, then we're shifting left and right. But if it's on the outside, it's up and down. And the left and right might seem counterintuitive. When we add 2, we're going in the negative direction, and when we subtract 2, we're going in the positive direction. But something we just have to remember is if it's happening on the inside, it's sort of backwards of what you're thinking, or what you ought to think. And so that's something we just have to keep working with, just like negative x, or it's like the negative h is positive h for the vertex form. It's another thing we just have to keep working with, and eventually you'll just remember that it's the opposite. So we're going to work with a couple examples. And so looking at this vertex form, Hopefully this should be solid for you guys, and you should remember how to do this. What is the vertex of this new vertex, or this vertex form, this transformed quadratic? -2, -7. And then looking at where these or looking at what has changed from the parent function of this quadratic, what are some transformations that we notice are happening in this quadratic? Oscar, do you see anything? Do you see any transformations that are happening or that you can see?
We're going
Down 7. Yeah, good job. This is on the back of your shifting quadratic functions notes that we were just working with. I'm sorry if I confused some of you by jumping around. Hayden? The other transformation we have is left 2. And we see it's down 7 because we subtracted 7 on the outside of the function, and it's left 2 because we added 2 on the inside of the function, on the inside of our square. And so, due to time management, we're not going to sketch these at the moment, but you can plot it on your calculator if you want, and then you can go back and you can sketch them on your calculator to see if you get it right. A way to do that would be to sketch your parent function and then just shift all your points to the left 2 and down 7. And that would be a way to sketch this function. So looking at our second example, what is the vertex of this function? Tiffany? +5, +2. So we take the opposite of h for the vertex and then keep the k sign. And then what are some transformations that are happening to this vertex, or to this quadratic? So we go up 2 because we're adding 2 on the outside of the function. And then what was the other transformation? Right 5. So we go to the right by 5 because on the inside of our quadratic we're subtracting by 5. And so we move our whole graph to the right by 5. Alright. So example number C, once again, what is the vertex from our vertex 4? Derek, do you know? Okay. Oscar? -6, 4. And then, Maddie, do you know the transformations that are happening to this one? Up 4, left 6. And so we see that's +4 on the outside, so we move up 4, and it's +6 on the inside, so we shift to the left by 6. And I'm hoping these seem like you can do them without having very much stress, because after yesterday and working with them today, I'm hoping you guys can look at this and understand it without having much fear with these shiftings. So let's do this last example. So what is our vertex? 2, -3. Good job, Tristan. And then what would the transformations be that's happening to this quadratic?
down 3, -2.
Down 3. And then right 2. And so because we have -2 on the inside of the function, inside the square, we're moving to the right by 2. Because we have -3 on the outside of the function, we're moving down by 3. So this next example, it should look similar to the quiz you guys just took, because we have a standard form equation and we need to get it into vertex form in order to find the transformations and the turning point of this quadratic. So just like how you did on your quiz, how do we get from standard form to vertex form? What method should we use? We need to complete the square. So that's the method that we want to use to transform our standard form equation into the vertex form. So what should be the first step we need when we complete the square? Oscar. We need to move our c. So our c is our -1, so we're going to add 1 to both sides. And we get y plus 1 equals x squared plus 10x. And then what is the next step we want to take when completing the square? We add b over 2 squared to both sides. In this case, b is 10, so we're going to add 10 over 2 squared to both sides. If we simplify this, we get y plus 1, which 10 divided by 2 is going to give us 5, and 5 squared is 25. And then so we have x squared plus 10x plus 25 because it's the same on both sides. And now we can simplify our left side. We get 1 plus 25 is 26. And then we need to factor our perfect square trinomial. So what are the factors of our perfect square trinomial going to be? Tiffany? Oh, sorry, I thought you were raising your hand. Oscar did.
Yeah, I got x plus 5.
So it's x plus 5 and x plus 5. Because 5 times 5 equals 25, and 5 and 5 combined to equal 10. Another way to remember is we can look up and see what we added, which was 10 over 2, and that's positive 5, and so we can do x plus 5. And because x plus 5 and x plus 5 are the same, we get x plus 5 squared, and then we just have to get y by itself. So we can subtract 26, we have y equals x plus 5 squared minus 26. So that is the vertex form of our equation. And so our goal is to find the turning point and transformations of our standard form equation that we got. So we just changed it into our vertex form so we can see the transformations. And then what is the new turning point, or what is the turning point of our quadratic? From the vertex form that we received. Tanya, do you know? -5, -26. And then what two transformations do we see happening to this quadratic? Matt?
Go left 5 and down 26.
What starts with L? So you go left 5 and down 26. We see that by the plus 5 in the quadratic, in the square, and the -26 on the outside. So down 26.